Okay, in this lecture I'm going to talk about heterogeneous catalysts. These are usually solids that accelerate reactions between fluid phase reactants. Usually they are like a fixed bed. The fluids are flowing over the catalytic particles and becoming products. Then that makes them easily separated. Examples of the actual heterogeneous catalyst material would include things like metal nanoparticles dispersed on a support, metal oxides and sulfides. Titanium dioxide and molybdenum sulfide are common examples of these. Metal atoms grafted to an amorphous silica or an amorphous alumina, or sometimes a high porosity alumina that's crystalline, like gamma alumina. Then you can have zeolites. These have shape-selective pores down at the molecular scale, and they can allow certain molecules in and not allow others in. They also have these solid acid sites throughout the material. Really incredible properties for chemical reactivity. One of the key features of a heterogeneous catalyst that's going to make it useful is it has to remain active and selective for hours or even years on stream. During its lifetime, each site may facilitate thousands or millions of reactions. And if you think about that, that requires a credible degree of selectivity. In many cases, the reactant stream, will have impurities and potential poisons. To make a commercial catalyst, this thing has to tolerate those and be able to remain active and selective in the presence of those things. One of the holy grails is that we would like to do all of this without using outrageously expensive metals. Okay, so our catalyst wish list is that we want a high turnover frequency. Turnover frequency is this acronym here, and that's really a measure of the rate. It's the rate normalized by the number of sites. We want a high turnover number, which is the turnover frequency multiplied by the lifetime. So this is going to tell you how many times each site how many times the catalytic cycle occurs at each site before the catalyst typically loses its activity. We want a catalyst that's robust to harsh conditions, and we want to be able to easily recover and regenerate our catalyst so that we don't waste expensive metals. Ideally, we would like to not use expensive metals at all. Okay, so if we look at the anatomy of a catalyst, a heterogeneous catalyst, we have the reactor scale where we think about the walls of the reactor. We have flows in and flows out. We have heat transfer coming in from the walls, perhaps. We have a packing that's often known as a packed bed or a fixed bed. And so this is the sort of 1 meter size scale. And if we zoom in on the packing itself, we see that there are interstitial spaces, there are the catalyst particles, and there are flows between them that are splitting and recombining. That leads to dispersion and greatly accelerates mass transfer and heat transfer. But also there are also internal heat transfer and mass transfer processes occurring inside these particles. And that can lead to gradients where maybe the interior of a particle is hot and the outside, this interstitial space, is relatively cool. Or, for example, where the concentration of a reactant at the surface is very high and the concentration in the center of the particle is very low, has been depleted by all the reactions happening between the surface and the center. If we zoom in even further and we look at these catalyst pellets, these things are maybe on the order of millimeters, but now we're going to zoom in to the micrometer scale. We would see that the pellets are typically highly porous. And really, when you look at the pellet, you're mostly seeing the support. So that support is a porous material, and this is depicting a little pore in that support, and alongside the pore walls, lots and lots of surface area to absorb little catalytic nanoparticles, or maybe to have chemically grafted sites onto the surfaces of these things. And what you see are complicated transport phenomena again, where compound A, your reactant, is diffusing down into the pore, it's reacting, and it has to diffuse back out as a product in order to complete the whole cycle, really. Now, if we zoom in even more, we would see the atomistic level processes happening on the surface of one of these nanoparticles. So we have lots of complicated things happening here. We have A molecules come in from the gas phase. They adsorb onto the surface. They might have to migrate as an adsorbate along the surface, and so you can get diffusion processes on the surface. You have maybe another reactant that comes in and reacts with surface adsorbed molecules. You then get products adsorbed, and then finally you get desorption steps. So these are all of these elementary level molecular processes that we talk about are pretty complicated, and they're all things happening down here at this scale. Okay, so this is where the actual kinetics happens. Way up here, when we think about the reactor, we have to think about mass and energy balances, and of course the reaction terms are part of that. But part of what modulates those apparent reaction terms are transport processes in between the two. Okay, so this is beautifully complex subject, but I think this is really an example of why we have these prerequisites and why this subject involves knowledge from all of the previous courses, right? So we have our mass and energy balances concepts at this level of the meter scale reactor. We have transport processes at the mesoscale. We have transport processes at the pellet scale, and then we have our kinetics, our actual molecular scale kinetics happening down when we look at the level of atoms. It's sort of, I think it's always quite enlightening and enriching to see how these all interact with each other at every scale and how you can self-consistently build one level of phenomena into a model at a higher level as you go up. And really, you guys have learned as undergraduates all the tools for doing that. We will be putting it all together in some of the worksheets over the next couple of weeks. All right, so let's begin to talk about the new stuff, the stuff you guys haven't really done in the past. And those are building overall mechanisms from multiple elementary steps. So this is the core of the kinetics, the mechanistic aspect of what's happening in a catalyst. So in all catalysts, all heterogeneous catalysts, you have adsorption steps. So we start out with some active sites. We have molecules in the gas phase. These come in and they bind to those active sites and they form an adsorbate. Now our notation for an adsorbate is that we use A, and we put a little asterisk here to note that it's bound to the surface. Okay, so this is our site with nothing on it, was a free asterisk, and then the A star represents an A adsorbate. Adsorption is a very important process because usually what's going to happen is that if you have very weak adsorption, like a physisorption process, that's not going to strongly alter the bonds in this reactant, and it's really not going to result in a easy reaction. What often happens in catalysis is that one of these first steps is a chemisorption step, and that means that new bonds are forming between the atoms in the reactant and the atoms in the catalyst. And by formation of those new bonds, we usually have some sort of a conservation of bond order, and that's going to cause other bonds in the reactant to be weakened, and those will be the ones that will be so-called activated bonds that will ultimately break during the catalytic step. So adsorption is often but not always fast, and cases where it's not fast typically are cases where you have one of these chemisorption steps. Okay, so when adsorption is fast, we're usually going to assume quasi-equilibrium for the adsorption step. For example, this is a dissociative adsorption process. Clearly, we have weakened a bond. In fact, this was H2 adsorbing to two active sites in this case to make two H stars. Now, this is completely broken the bonds between H and H here. We now have two separate H star entities on the surface. So this is definitely a chemisorption. And on most metals, this is going to be an activated process itself, okay? So we wouldn't say that this one is quasi-equilibrated necessarily, but if it was just H2 coming down and sticking on some surface through dispersion interactions, then that would probably be a quasi-equilibrated step. By the way, H2 has a very hard time sticking to anything by dispersion interactions because it's a small and nonpolar molecule, and that means that it's not going to have very strong dispersion forces. Let's talk now about surface diffusion. So once you have an adsorbate on the surface, sometimes these things can migrate along the surface, and in many cases these processes are slow. You have configurations where the adsorbate likes to be sitting, and in between two configurations where it would like to sit, there's a little barrier to jump over. And so these surface diffusion processes are often activated. If you look at the diffusivity, you often see something that looks like an Arrhenius law, a strong temperature dependence of those. In many cases, that can become important. Let's also talk about unimolecular surface reactions. So this is a case where you have a single adsorbate attached to a surface, and it's going to undergo a reaction that transforms it either into another adsorbate or another adsorbate minus some species that is kicked off into the gas phase. Okay, so that's the generic notation for one of these unimolecular surface reactions. And a real-life example would be this alkyl fragment reacting to form, to do something like a beta hydrogen elimination to give you an H on the surface and an olefin. Okay, so this is something that's common in a lot of polymerization reactions. This would be like a termination step for one of those. Okay, so the polymer comes off like this, and now you have a new chain ready to grow right here. Another example of an elementary step that can happen in catalysis is something that we would call an Eley-Rideal reaction. So in this case, you have an adsorbate on the surface, and it's going to directly react with a molecule from the gas phase without a preliminary adsorption step for the molecule from the gas phase. So if these two interact with each other directly without first becoming A star and B star on the surface, then that's an Eley-Rideal type surface reaction. And an example of that would be oxygen atoms on the surface, oxygen adsorbates on the surface, reacting directly with CO molecules from the gas phase to liberate a CO2 molecule in the gas phase. And I should balance this equation to be careful here. What we are left with is a free surface site. Let's talk about one more type. We have Langmuir-Hinshelwood surface reactions. And in this case, you have, so Langmuir and Hinshelwood did a lot of stuff in the area of catalysis, and you will see their names attached to a lot of different things. In this case, Langmuir-Hinshelwood reaction refers to a case where you have two adsorbates on the surface already, and they're going to react with each other. Obviously, they have to be kind of close by in order to do that. That can have important implications itself. But here's an example. Hydrocarbon fragment on the surface and an H atom on the surface, and it's going to react to give me an ethyl fragment and a free site. Another example is two oxygen atoms reacting to liberate O2, and again, I should balance this equation. I free up my two sites again when I do that. Okay, don't forget species, even when there's just a free open site there. Lastly, let's talk about product desorption step. So in many cases, we end up with a product adsorbed to the surface, as we saw up here in this one. You know, that's a product of this reaction, but if it can't desorb, it's going to build up on the surface. And eventually, if it builds up to the point that it covers all of the sites, then the catalyst can't do anything anymore. So desorption can be a very important part of the process. It can result in poisoning if you can't desorb your final products.